Hello guys. So today we're gonna talk about the voltage references. And as you know, I made a previous video about the TL431. It's one of the most voltage references and it costs even a low price, just 50 cents around that. And you know that this guy is basically a shunt regulator low side with a reference voltage fixed to 2.5 and the if you provide a bias current of 1 milliamp with resistor and you have two resistor, let's call it R1 and R2, you already know that the equation is this is Vref, this is VO, and VO for the divider is equal to VR is equal to R2 times R1 plus R2 times VO. But as I said in the previous video, in a feedback system, because this is a feedback system, because the TL is basically an op-amp with a transistor, like this, okay? And so you control the feedback point. And so VR is fixed, and actually you have the opposite. VO is equal to VR times 1 plus R1 over R2, which is the same equation of every reference voltage system basically, or even the same equation of the inverting op-amp, non-inverting op-amp. So I won't get into this video because I already made this video of the TL431, and now we can instead explore three different techniques. The second one is the Zener diode. You have a bias resistor, RB, you have a voltage, V logic, and you have the Zener diode. And this is going inside an op-amp, in the plus, and in the minus, I don't know, you have some kind of divider. We can make, for instance, an application in power electronics for the overvoltage application or something. Okay? So, basically this is cheap. So the cost of this guy is 1 cent. Around that. You have fixed voltages, 6.2, 5.6, something like that. But there is a problem. It has a brutal drift in temperature. So the voltage reference will increase with temperature, and that is not good. So it is a cheap solution, but in some application it might not be recommended. The third solution instead is to use a microcontroller, and this is very useful when you have to implement a dynamic reference. So you have the microcontroller, you generate the PWM, and then you filter with an RC. What you obtain is this graph here. Now, two important points. First, you notice that there is a DC component. This DC component is directly proportional to the duty cycle D of your PWM. The higher the D, the higher the duty cycle. Sorry, the higher the duty cycle, the higher the DC component. Well, you can imagine that. And why is that? Because basically, the higher the duty cycle and the more voltage it is constantly applied to the capacitor. That's it. Now, so this is the first point. Second point of this, the ripple. The AC ripple basically depends on the RC. If your RC is more robust, then you're gonna have less ripple. But you have to pay a price. And the price that you have to pay is the speed. So, if suppose that we have the same duty cycle but a stronger RC, you're gonna have something like this instead. So you're gonna pay in speed. This is the second rule. This is the and this is the third feature. The third feature. So this is also a cheap solution and useful when you have to implement the dynamic reference. So you can imagine that after this, the information coming from an op-amp goes inside the microcontroller. You have a script, okay, LL something, and then he will modify the duty cycle accordingly. Very powerful, very cheap, very useful. Then we have the last method, which is a bit expensive, but also used in analog integrated circuits. So basically you have the MOSFETs with the gate shorted, voltage here, and the other MOSFETs in the saturation region. You short the gate with the drain, like this. And this is shorted to ground, like this. The result is basically that you are exploiting the VTH of your MOSFET, which is quite stable, but not stable enough to be used as a real voltage reference. Yes, you can use that, but you have to be more and more precise and compensating stuff. So this is just the main building block of a voltage reference. The real voltage reference can look like this. You can recognize the main block, which is the saturation region of the MOSFETs. Then you can recognize the current mirror, the differential stage, and also the compensation capacitor are there. So the powerful thing about this one is that you can use whatever configuration that you need to compensate as much as possible. Now, just a quick note, if you didn't follow any class of integrated electronic circuits, but this is not a fraction, so this 100/1 is actually the ratio between the width and the length. This is the width of the MOSFET, of the channel MOSFET, and this is the length. So just a quick tip. What does it mean? Basically, this is the dimension of the MOSFET. A number can be one micrometer, or I don't know, 500 nanometer. These can be numbers, okay? And secondly, the higher the MOSFET, the higher the current on the same VGS, because the equation of the drain current is proportional to V double over L times VGS minus VGS VTH square. And what about the length? The higher the length, the longer the length, and the more ideally behaves the MOSFET. You do remember that when you had the short length, you had terrible equations, okay? The long channel approximation is one of the strongest and beautiful approximation that you can use in electronic devices. So we will use also this simulation LTSpice, and we will compare each of this method in temperature. But of course, we need a benchmark, we need an application of this stuff. So we will design an overprotection system. So let's open LTSpice and don't waste any time. Let's start with the diode and let's put the Zener configuration. Let's select maybe the first one, so 6.2 can be enough. Okay, let's make comment here, and let's put a bias resistor of 1K. This we call RB. Then we select R1, R2, which will be our feedback coming from the output. Let's suppose that this is the output of the DC converter, which has reached a problem. So it is another protection OVP benchmark reference components. Okay. We want to implement an op-amp working as a comparator, so universal op-amp 2 can be exactly fine. And we put the reference on the plus. This should be 6.2 if everything is correct, and the divider on the minus. Now we suppose that we have also the logic, the V logic. Of course, the V logic. Sorry. There is a big difference between these two. So the Zener diode is connected to the logic. Okay, of course, you don't connect the Zener diode to the power. Okay, the logic is the logic can be even, I don't know, 15 volts, 14 volts, something like that. And this guy is connected here, but the divider is connected to the power. So this is the V power which can be a very high voltage in the first place. Let's suppose that it is just a ramp from 0 to 100 to 70, something like that. The rise 1 milli, 1, 2, 4, don't care, honestly. So we connect the divider to the power. Now we need to design the divider. Of course, don't forget the capacitors. 1 micro. And okay, so this is the power voltage, and what do we do here? We have to design the divider for this overprotection. Okay, so let's suppose that we want the overprotection to be triggered at V equal to 50 volts. We use the same equation that we used here. So we know that this is a system of equation. VO is equal to VR times 1 plus R1 over R2. VR is equal to 6.2, and we know that VO is equal to 62, just because I want to make some the stuff easier. Okay, so now we need to solve this equation. We have that VO over VR is equal to 1 plus R1 over R2. So R1 over R2, this implies that R1 over R2 is equal to VO over VR, which is 10, and R1 over R2 is equal to 9. So we have that R1 is equal to 9 times R2. To solve this equation, we need to impose the value of R2, which is 1K, and R1 is equal to 9K. Let's verify the solution. So we have 62, which is equal to 6.2 times 1 plus 9 over 1. This is 62, which is equal to 6.2 times 10. Okay, it's correct. So now we can use these two values. 9 times R. And you see that the equation does only depend on one parameter. Okay, so 9 times R and R. And so I say dot param R equal to 1K. So automatically this is set to be what I need. So I can run the simulation with a step with just 1 milli, and just of course the names of the net. This is the reference voltage, and this is the power node, and this is the output node, which will go into microcontroller. Let's save this guy. Let's use the reference voltage benchmark, OVP. Yes, replace it, save it. So we have the reference, which is a 6.37. Okay, so this is a little bit different that we calculated, but it's no matter. The power, okay, and better to use the feedback one. Okay, so at this point we expect to go down, and it works. So at what voltage we have the power? We calculated 62. Now let's see. The trigger is around 64. Ah, not bad. Okay, not bad. It's good. Yeah, the difference is because this is 6.2 according to SPICE, but in reality it's not. But what's the problem? So this is the over problem. This is over protective over voltage benchmark. But I want you to see the quality of the reference voltage. To see that, we open another LTSpice and let's call it temperature benchmark. And the temperature benchmark does only take this part here, which we will confront also with the others, and just use the reference voltage varying in temperature. So what we need to do is to use the command .dc temp -20 150 and save the file as reference temperature benchmark, and we run it and we see it. So actually the reference voltage is changing with temperature drastically, and this is not good, because in precise voltage application you need that to be precise, and this is not the best. Let's leave the temperature benchmark as it is, and now let's move this little guy away. So we tested the first. Okay. Now the second one. We said that the second one was the microcontroller method. So let's take a PWM. Let's call this guy PWM. And let's suppose that the param is D is 0.9 and the switching frequency is 150 kHz. You already know the story. Just what pulse 0, 3.3 volts is reasonable. 1 nano, D over Fs, and 1 over Fs. You know the stuff. Now, we need to implement a low-pass filter for this. So let's put for now 10K. Whoa, too much. 10K and 10K and 10 nano. And this goes inside the reference. Now, let's run the simulation. And what we see is basically that, let's close this for a minute. You see that the ripple is very low. Okay, so you notice the three things that I told you: the DC component, the transient, and the ripple. And all of this depend, and the DC component depends on the duty cycle. How can you see that? Dot step param d list 0.4, 0.7, and 0.9. If I press run the simulation, you will see the different values. So as I increase d, the reference increases, as I told you. So nothing new under the sun. Let's just use dot step d equal to 0.9. Now, dot param d. Oh, come on. Dot param d equal to 0.9. Thanks. So now, what about the AC stuff? The AC stuff is influenced by the corner frequency of the low-pass filter and the switching frequency itself, because of course they are related. So if I put, for instance, a higher switching frequency by keeping the same filter, of course you will have a less ripple. You know the story. The higher the switching frequency, the lower the ripple. You already know the story. So if I put 100 kilo, you will see a different ripple, a very high one. Not very high, still acceptable. But if you put instead, if you keep the switching frequency fixed, like in this case a microcontroller does, and you change, for instance, let's put this value to RC, and we say dot step param RC list 1K, 5K, 10K, 100K, and you press run. You will see that there are not only different kind of ripple, but because we are changing the filter, but also different response. So the stronger the filter, the slower the response, and the less the ripple. you have to find a compromise between speed and ripple. Okay, it's not that a very high ripple is gonna kill you. Okay, so let's see, for instance, you see that here you have the point of interest. So let's see what happens to the output of this guy. It's not that okay. At a certain point, it starts to do something bad, and he's probably the first. So if I cancel this and just put 1K, it's probably gonna be very, very fast, but with high ripple. Yeah, that one, the first, probably. And it's going to, okay, so it's doing something bad. And this is because this is an ideal op amp, but if you use a real op amp instead, you will see something maybe mm, 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 mm. What's this? Mm, not so beautiful. And if you reduce the capacitor, no, 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 no. So you can't have this kind of ripple. Okay. Clearly you can't have this kind of ripple because you see what this guy is doing. It is fine. A response like this, it's fine in your opinion. Do I need really to comment this? So, guys, just please use common sense. In this case, 3K. In this case, 3K 10 nano is good. Okay, or 2K 10 nano is good. Okay, just use common reason, and this is fine. So let's put this guy aside. I just want to cancel the PWM because it slows the simulation down. Okay, so I just put the RC filter like this and just put a 0, but you know that this is a PWM. Okay, so don't. Why it doesn't work? Please. So now let's use the third one, and actually it involves the two MOSFETs like this. So the first had let's pick the first of the list. The first had the ground at the gate, and the second had the short between the gate and the drain. Now this one should give around 1.6. Let's verify it before running the simulation, and it does 1.65. Good. So now let's take the reference and let's connect it to that. And what we see here? What do we see? Something which is not good. So the behavior of this, it's actually changing with time. So it's something this is not so absolutely not so beautiful. Okay. And so aside from the fact that the output voltage goes down almost immediately, it is not a good reference the moment you connect it directly with an high impedance source. So for this reason, to really use this stuff, you should do something else. Okay, it's almost never used as a discrete MOSFET, but as I told you before, it is used in integrated solution like this one. There is no reason to simulate this. You can have a more appropriate simulation if you use the NMOS4. I did something like that in the past. As you can see, you can set the length, the width, the area, the end area, but you have to know your stuff, because if you just short like this, okay, we can try, but we can try. We can try to do something like that, but this probably is not gonna work because you don't have any kind of data. You don't have any kind of data to select the reference or something. So it's basically a blind MOSFET. And in fact, you have just 1.70 millivolts. You had to select some MOSFET. So for instance, to 1 micro or 2 micro. No, this is 10 nano, for instance. This could be, don't know, 1 micro, something like that, probably. But then you have to know also the other parameters. Yeah, it has increased a bit, but you have to know also the other parameters. Per device, let's put 100, but I repeat, you have to know the parameters to do something like that. So I don't want to waste my time in doing this stuff here. So, but by the way, let's return to the reference temperature and let's really put these two MOSFETs and let's see, supposedly that this is gonna work fine. Let's see how does they change actually with the temperature. So let's see how this configuration actually change with temperature. So we have, let's call it VREF1 and let's call also this node VREF2. So let's see which of them is more stable. This can be interesting. It's a comment? It was not a label? Really? So this is VREF and this is VREF2. Now, if we run the simulation, we might see something interesting. Let's see. Delete this pane and delete this stuff and run the simulation. Okay, this is VREF and this is VREF2. Oh, so actually, it is more stable than, even if you use this block here, it is actually more stable than the reference diode. That is interesting because the variation is between 1.69 at -20 and you have 1.59 at 120. This is interesting. And what about this little guy here? You have between 6.34 to 6.43. Yeah. So in the end, it's almost the same. The problem is that this is very expensive and this is not. But as I told you, in order to use this method here, you have to compensate it properly with all this stuff or other analog stuff. So I hope that you are quite satisfied with this kind of application with the Zener diode and the PWM stuff. I hope that this video has enlightened you. And I have officially transferred in Munich, by the way, so I'm not anymore in Italy. I am still a power electronic designer, and let's see each other again, guys. See you in the next video. Bye bye.